All right. Hello and good afternoon, everyone. So welcome to the first Summer ECE Wireless Distinguished Lecture. We are all excited to start this series in the department this summer with a lot of distinguished speakers pretty much every week from now on. So it is our great pleasure to kick off this series with our distinguished guest today, Professor Kyle Jamieson from Princeton, who is actually well known by a lot of wireless and networking folks here at Rice. Dr. Jamieson is an associate professor at the CS department at Princeton, and at the same time, an honorary reader at University College London. So he received his bachelor's, master of engineering, and PhD in computer science, all from MIT. He also received a starting investigator fellowship from European Research Council, a Google Faculty Research Award, and the ACM SIG Mobile Early Career Award. Currently, he leads the Princeton Advanced Wireless Systems Group with his research focusing on building mobile and wireless systems for sensing, localization, and communication that cut across the boundaries of digital communication networking. So the title of his talk today is End-to-End Congestion Control via Endpoint-Centric Wireless Physical Layer Capacity Measurement. So before we start the lecture, I would like to ask the audience to please write your question in the Q&A section during or at the end of the talk, and I will read them to Dr. Jamieson to answer. So with that, I would like to once again welcome Dr. Kyle Jamieson. Please, floor is yours.
Okay, thanks, Raman. So, right, so today I'll be talking to you about, and thank you very much for having me with your in this first distinguished lecture. So today I'll be talking about congestion control, and it's a really well-trodden area, but this comes out of work in collaboration with one of my postdocs named Yashong Xie at Princeton University, and Yashong is responsible for the Athros CSI tool that many of you have used in your Wi-Fi experiments. And he recently became interested in congestion control in cellular networks. And so what I'll tell you about today is something it's going to come up at this year's SIGCOM in a paper, and it's about using very precise cellular capacity measurements to drive end-to-end congestion control. So let me kind of elaborate on that, and can you move to the next slide, please? All right, so end-to-end across the entire internet, what we're looking at is downlink data flows that you might be using for Netflix or interactive video or just bulk downloads surfing the web. And more and more these days, those flows are terminating at a wireless last hop, because more and more of our devices are wireless. We're connected even in our homes via Wi-Fi, or we are connected via the cellular network. And so it's actually the last hop, the wireless last hop, that's doing most of the damage as well to data flows in terms of losing packets, in terms of slowing down, and in terms of the rate of that and the capacity of that wireless last hop. And so it's really worth focusing on that wireless last hop to see if we can improve the end-to-end data flow. So at the end of the day, we will be looking at the metrics that are end-to-end and are essentially asking the question, how well is Netflix working, or how well is my Zoom webinar working when I'm giving it on a mobile client and I'm talking to a server all the way across the internet. And so the position we take in this work is that if you believe that wireless is there most of the time, and you believe that that wireless is the bottleneck, and it does the most damage, then you kind of should believe that the endpoints themselves, which are right next to and participating in the wireless link, the endpoints themselves are the ones who are best positioned to measure wireless congestion. Um, and I'll give more arguments as to why I believe this is true later on. But I think the observation on this slide is that the endpoints themselves form half of the wireless link, communication link. And so if we can take really, really precise measurements at the endpoints themselves of what the wireless is doing, then we can build a transport, an end-to-end transport protocol that is going to have the server send at exactly the right rate to maximize throughput and minimize the latency of the data flow. And that's really what the goal here is in all this wireless congestion control work, is to maximize throughput while simultaneously minimizing latency, so that your interactive applications, your web surfing, your apps, your video conferencing is all performing very well, because that is all very sensitive to latency. So throughput and latency are the goals here. Okay, right. So the picture looks like this, and we're looking at, let's see, a picture looks like this. We're looking at the server sending at some rate to the mobile client, and somewhere along that path from server to client is going to be some bottleneck capacity. And that's just the capacity of the slowest link on end-to-end from the server to the client. And when we send below, next slide, next animation, if we send below the bottleneck capacity, we will be underutilizing the rate. So the round trip time we see is going to be roughly just the end-to-end latency without any queuing, because queuing isn't happening yet, because we're sending slower than the bottleneck can hold. And so this is an application limited regime, if you will, or it's where the application knows that it shouldn't be sending faster than that bottleneck. So this is where we want to operate. And next animation. And so this is where we want to operate. This has actually been studied by Kleinrock as the optimal operating point of the network, where we're sending and not building up queues. And if we start to send, next animation, faster than that, we'll be overutilizing. And next, please. And we're reaching a point where we're overutilizing the network, and so queues are starting to build. But of course, all the routers and switches in the path from server to client have some kind of buffering available to them. So at that point, we are building up packets in buffers, and our round trip time is experiencing an additional delay that is due to all the queuing of all the packets in the buffers just before the bottleneck of the path. And next animation. So we're bandwidth limited, and if you keep going with the animations, then we reach a point where eventually buffers start to fill, and we must drop packets. And so latency is sky high. We don't want to be operating in this point. We're sending just far too fast for the network. So next slide, please. So back in 2016, Google showed that, and other work as well as Google's BBR showed that we can do pretty well in terms of converging to Kleinrock's the optimal operating point in terms of matching the sender's rate to the bottleneck capacity. But this was mostly studied in the context of wired networks. And in wired networks, traffic is bursty, but it's not as bursty as wireless networks are. And so the approach that BBR takes to converging on this optimal capacity is uses very coarse-grained signals and relatively infrequent signals. So the approach it uses is end-to-end measurements. It's looking at when the packet was transmitted using round-trip timers. It's looking at whether the packet was received or not based on sequence numbers. It's looking at the sizes of packets, and it's merging all those signals together in a formula to try to estimate the bottleneck capacity and whether the sender is sending at the bottleneck capacity. And all of these signals are rather infrequent and they're pretty imprecise. So they need to be averaged out with very long time averaging windows. And the result is that that while BBR converges to the Kleinrock's optimal operating point, it doesn't do so very fast. And so when the bottleneck capacity itself is changing really quickly, we can do better. And here's why. So next slide, please. So wireless capacity, as many of you know, is going to vary very significantly in cellular networks. So why is this? Well, cellular networks use a physical layer called OFDMA, and many of you will be familiar with OFDMA, but the salient feature that you should think about is how OFDMA is able to be very, very agile in terms of quickly allocating bandwidth to one user or the other. And so subframes, or the units of bandwidth allocation in OFDMA and cellular networks, are just 1 millisecond long. And so contrast that to like an internet propagation time of 10 to 30 milliseconds. And you can see that the number of frequency blocks that OFDMA can allocate to users can fluctuate many, many times just in the process of a few round trip times on the internet. And furthermore, what you're doing within each physical resource block is also determined by the wireless channel quality. And so you might be sending fewer or more bits within each of these resource blocks. So estimating capacity is really, really very hard, and it can vary very rapidly. And the first reason is OFDMA. Next slide, please. And if you keep going to slide 10. Next, please. Yes. Okay. So capacity varies rapidly because of OFDMA, and it also varies rapidly because of just fundamental structure of wireless networks. So users are competing with each other, just like they are in wired networks. But crucially, users are moving around frequently, right? And so that's going to change the wireless channel quality. It's well studied markedly with rapid fading in and out. And that's going to make OFDMA react by sending fewer or more bits, and that's going to exacerbate the swings in capacity in cellular networks. And then the other interesting thing that cellular networks do in particular is this thing called carrier aggregation, where multiple base stations are going to cooperate to serve the same user, to flow data to one user over multiple different frequencies that each of the base station is on. And this can get even more sophisticated with multi-user MIMO and coordination between base stations. But even what's out there today in terms of carrier aggregation has many base stations transmitting to one user at the same time. And this can be switched on and switched off very abruptly. And so the user might see, close to double the capacity when carrier aggregation is switched on within the span of just one subframe, 1 millisecond. So capacity doubles in the span of 1 millisecond. And wouldn't it be nice if the end-to-end protocol could see this and react to it very quickly? Next slide, please. So that's kind of the first leg of the work that I'm talking to you today about, is the ability to see that abrupt change in capacity, wireless capacity, and react to it very quickly and grab that bandwidth and have the sender use that bandwidth productively as quickly as possible. And so the first leg of that is some kind of functionality where the wireless device is going to monitor um, all these cell towers that are nearby the wireless device. And now you can see why I'm making the case for this monitoring to be happening at the mobile device instead of perhaps the cell tower, or elsewhere on the internet or the server or somewhere else. Only the cell device, only the mobile device gets the first notification that it has more capacity um, from multiple cell towers, and so it's in the perfect position to snoop on what's going on the air around it, and see what capacity the cell towers have allocated to it, and what capacity the cell tower has allocated to other users, and what capacity is still idle and available to be used. Um, and so we've developed this mobile monitor functionality to implement that. So it's looking at the control channel, and I'll tell you in a second some more details about how it works. But the takeaway points are that it doesn't require any changes to the cellular network infrastructure itself. It's living solely on the mobile device, and it is in snooping on unencrypted control channel information. So it is deployable as well. Next slide, please. Right. So some more details about the control channel decoder. So in terms of decoding control messages, usually mobile users only decode their own control messages. So what they have to do is they have to run a kind of a search in the space of physical resource blocks in the control channel to find the control messages that are destined for them and the control messages that are destined for other users. And so part of the work of this project was to make that search, to really optimize the search for every user, so that we can decode the messages that are bound for every user and extract the capacity readings for each user. So next slide, please. Okay, so our congestion control design has the mobile, the physical layer of the mobile looking at those control messages, and then figuring out a fair rate that the sender should be sending, and then stuffing that rate into the feedback packet end-to-end that's going back to the server in terms of the the ACK packet that's going back to the server. And so what we have is a traditional congestion control protocol. It's similar to TCP. It's similar to the work that Dina Katabi and co-authors did on explicit congestion control, the XCP work, and other people have looked at explicit congestion control as well, in that we are having the mobile client tell the server explicitly the rate that it should be sending at. Now, the wrinkle happens when you don't have control over every single router on the path from router and switch on the path from server to cell tower to mobile client. And so an explicit rate control protocol like XCP out of the box, it needs that control and modification over every single router on the path, and we don't. And so however, we have to kind of get around that um, in a way that I will talk about next. So next slide, please. Okay, so now let me explain to you how we estimate the capacity of that a user should be, the sender should be sending at the receiver. So suppose like a connection opens fresh. Well, then the wireless endpoint needs to be looking at the total capacity available at the base station or multiple base stations, and it needs to be looking at the number of mobile users that are also sharing the bandwidth at the base station. So that number n, the mobile client can get by listening to the control channel, and it will overhear the control messages destined for other users. So we have a kind of a scoreboard that keeps track of those other users. And then it's looking at the number of physical resource blocks that are available, and then it's taking a fair share capacity of that that's time fair. So if if one of the users is far away from the base station, is only able to send at a slow rate, you can define fairness how you like, but a popular way of defining it is by having the connection be time fair so that everyone gets an equal amount of time and can send as many bits as they can in that time. So next slide. So if you go to slide 15. Right, so that's an example of this. Suppose user one is all alone. So it's going to grab all the available bandwidth. And this is nice, right? So at connection start, the wireless client can see how much bandwidth is available, and then try and have the sender grab that much bandwidth. Also subject to starting the connection from the perspective of congestion on the rest of the internet in a gradual or relatively gradual way. So next slide, please. Right, so now suppose some other user comes along and opens up a connection. In that case, both users see each other through the monitoring, and they can calculate their fair share bandwidth, which will be half, and so they equally share the bandwidth. Next slide. Right, so that was at the start. So now let's talk about how things evolve in the steady state when connections are open. So there, flows may stop, and that results in physical resource blocks becoming idle. So if you have a scheme where you take everyone is detecting and noticing those idle resource blocks, then that's idle wireless capacity. So what they can do is take what they have been allocated currently, and they can grab additional bandwidth equal to their fair share of the idle capacity, which is the idle resource blocks divided by the number of active users. So if you go to the next slide, right, number of users is going to increase, and the number of and then those users will track and adjust their fair share to share with 3 users instead of 2. Next slide. And now user 3 stops transmitting. Next, please. And then at that point, users 1 and 2 will see those idle resource blocks, and as I said before, they will divide up those idle resource blocks and grab their fair share bandwidth, which again is half for 2 users. Next slide. Okay, so now if user 3 restarts its transmission, again, we go back to fair sharing. Next, please. And the same thing happens if the third user doesn't stop transmitting, but instead, if it slows down its transmit rate, next slide, the two users can grab their fair share portion. So it's flexible in terms of um, offered load of the users and grabbing idle bandwidth. Next. Okay, so as I said before, when we have a situation where multiple base stations are cooperating to serve a single client, um, then the capacity that is available to that client is going to be a summation of all the capacity available in those OFDMA resource blocks from each individual base station. And so we can adjust our calculations for carrier aggregation as well. I said before, the goal of congestion control is to match the sending rate to the capacity of the bottleneck. But so far, my discussion was kind of making the assumption that the bottleneck was in fact the cellular wireless link. And the literature and our experiments indicate that most of the time that is actually true. The bottleneck is at the wireless link. Sometimes, though, the bottleneck could fall back in a wired internet link if one of those internet links is especially busy, for example, or misconfigured or something. And so, we have this slight problem that we don't want to break that scenario and overwhelm a bottleneck that might arise on the internet. And so far, I've only talked about estimating wireless capacity with the the wireless physical at the information at the last hop. Next, please. So, so if we, and this is just sketching out what I said before, if we just match the wireless capacity, then we're going to start to overwhelm. There's a problem with the formatting, but I'll just say what's going on. If we just match the wireless capacity, we may start to overwhelm bottleneck links in the internet. Right. So we're continuing along with our wireless precise congestion control. And how are we going to detect when the bottleneck changes to an internet link? So there, we're at the mercy of the internet, hiding everything that's going on. And so the best course of action for us in this rare event, it's pretty rare, but the best course of action is to essentially look at the same signals as BBR and other algorithms are doing in terms of the delay. And so the warning that we will have when the bottleneck changes to the internet itself is that that we're building up queues in the internet is delay. But in cellular networks in particular, we have this significant jitter that's often on the scale of 8 and 3 milliseconds. And I'll say why this happens. But we don't just want to react to any old sudden increase in delay, because it probably would not correspond to a real bottleneck change. So just studying, jitter in cellular networks is something that we had to do in order to understand the problem at hand. So so we looked at different offered loads, and the observation is that when the sender starts increasing its offered load from 6 to 24 to 36 megabits per second, you can pretty well pick out the minimum one-way delay of that connection. And you can also pick out more and more jitter. You can also notice more and more jitter as the send rate increases. So why is this? Right. So what's happening is packets are coming in at um, the transport layer. Packets are coming in at the physical layer at the receiver, and they're going into a reorder buffer. And only when that reorder buffer contains contiguous packets are those physical layer received packets delivered up to the transport layer in order. And this is necessary because we want to keep this is what the cellular network does, right? And why does it do this? Well, it wants to keep the physical layer busy. It wants to keep the wireless medium busy. And so it's allowing itself to go on to later packets if some of the physical layer packets are dropped because of noise or mobility or whatever. And so these retransmissions start to delay packets. Next slide. In addition, we're trying to estimate the wireless capacity, and so we have overhead data protocol headers. Different parts of the physical layer are putting of the link layer and the physical layer are putting their own headers onto packets. Next slide. And so we're in a situation where the amount of overhead as well that the cellular network is adding starts to increase because when we and it's a function of offered load, and this is something that our measurements kind of realized, and it was kind of surprising to us that this retransmission overhead was a function of offered load. And the reason this is happening, we believe, is as you increase the offered load, the cellular network starts to build bigger and bigger transport block or packets at the physical layer. And when you have a bigger packet with the same amount of error correction, you're going to get a higher and higher error rate or frame error rate of those packets, and that will lead to more retransmissions. And so you have this interesting result, and our experiments kind of matched the theory that that this would have you that this would predict would happen. So that kind of bolsters our hypothesis that this is what is in fact happening. And so next slide. And so what we do is we want to translate between the number of the amount of physical layer capacity available and the amount of transport layer capacity available, so that the sender can send back that information, the receiver can send back that information to the sender and have it send at the right rate. And so our calculation factors into account the transport block error rate as well as the transport block size to have the sender send at a sensible rate. Next slide. Okay, so going back to jitter, just to walk you through an example of how this happens. So if everything goes according to plan and the transport blocks are received correctly, then those just get delivered up with no additional latency penalty. Next slide. Right. So now, if on the other hand, if blocks get lost, then subsequent transport blocks get delayed. Next slide. And so they get sent instead into a reorder buffer. Next, please. Only after the base station or the receiver has had some time to process and receive the transport blocks, does it send back a NAC and have the or LACAVAC and have the original data retransmitted. And this is so that we can keep the medium busy. And this is so that the base station can do the processing required. So it's giving itself 8 milliseconds to do that processing. And then 8 milliseconds later, that retransmission happens. And if that retransmission is successful, then next slide, then everything gets delivered in order, but it gets delayed by that 8 millisecond multiple. Next slide. 8 millisecond delay because of that retransmission. Next, please. Okay, so we're looking at an algorithm where we take we don't look at the minimum one-way delay when we want to set a threshold above which we will call the switch in the bottleneck. And so instead, we look at some number of retransmissions to give ourselves protection against this mechanism. Next slide. Okay, so if you look at what BBR does, then over time, it is it's dividing time into 8 or some number of phases, as you see in this picture here, and it's adjusting the rate that it sends. And each one of these steps or these phases that you see in the picture is an entire round trip time long. So it's a very, very slow process. So what BBR does is it is adjusting the sending rate, and the numbers you see are the pacing gain. So it's estimating capacity and it's increasing rate, and then it's looking at and seeing what's the latency impact of increasing the rate of the sender, and then it's trying to probe for more bandwidth, and again over RTT length intervals, and then see whether and try and drain the queue and converge to a state where it's taking up the bandwidth. Next slide. So we take that BBR algorithm and we kind of do a smooth switch over to that probing mechanism when we see that queues are building too much when we're running the precise congestion control that's on the wireless bottleneck mode. So we switch, and then when we're doing this, we if that BBR probing mechanism reaches a point where we actually achieve the wireless capacity, then we know we're back to a case where it's wireless that is the that's the bottleneck. And in this situation, we switch back to the wireless bottleneck mode, right? So I'll spend just 5 or 10 minutes talking about implementation experiments. So we actually built this. We built this on a software-defined radio as a USRP, but everything that we built is purely mobile side, and so we argue that it could easily be implemented in custom cellular firmware. And the algorithms that we run on the host associated with the software-defined radio, they're not much more. I can talk later if offline if anyone's interested in more details. But basically, they're not much more computationally intensive than what's already going on in the wireless firmware. And so we argue this is really practical for a real deployment if one had access to the wireless firmware. Next slide. So we're looking at Amazon Web Service servers as the senders, and they're sending to 3 different mobiles, some of which are using carrier aggregation. So some of our mobiles are talking to multiple base stations, as you can see in the picture. We're comparing against all the recent algorithms. So some of those, Sprout and Varus, those are designed for cell networks. The cutting edge in the Linux kernel, BBR and Cubic, and then the cutting edge research schemes, COPA, PCC, PCC, Voace. Next slide. So Looking at now CDF of throughput. CDF is across different locations. The CDF is BBR as a baseline. That's the black curves you see. And then for each location, the scatter points are telling you how well we did at that exact locations. They're paired with the BBR CDF curve. So it's kind of a bake-off or a comparison, a direct comparison across each of our 40 locations, each of which is a CDF point. So you see that a lot of the time we're doing better in terms of throughput than BBR. Sometimes we do worse, excuse me, but not often. And at the same time, we are doing significantly better than Cubic and Veris. And the win, though, experimentally, is simultaneously at the same time we're cutting latency on the right-hand side plot. You can see that we are reducing latency. So left is better on the right side plot. So you see that we're significantly reducing latency, just like Cubic can, except we're getting much better performance in terms of throughput than Cubic does. So essentially the argument here is we're getting the best of both high throughput and low latency, which is very important for, say, interactive applications. Next slide. So this is the same take-home message, but showing you more summary statistics. So you might be wondering about how well this works indoors. We also have outdoor experiments. How well this works when you turn up the number of aggregated cells to 1, 2, or 3. That's very common, it turns out. And so how well this works, whether the network is idle or busy in terms of background. So we're looking at throughput versus delay. And the box is showing you the confidence intervals of both. And we are in red. And essentially the same take-home message, we're simultaneously getting good throughput, better throughput, and lower latency than all the comparison schemes. Next slide. Okay, so digging into a bit more why this is. We looked at static users, and this is both busy and idle hours. But why are we doing better in terms of throughput, and why does also Veris and BBR do better in terms of throughput? And a big reason for that is that these algorithms, ours, Veris, and BBR, are successfully triggering carrier aggregation. And when you trigger carrier aggregation, you turn on 2 and 3 base stations to serve a single user. And so your throughput goes up significantly. Whereas if you don't send aggressively enough, you never trigger carrier aggregation. And so, Cubic and Copa and Sprout fall into this category. They're not aggressively enough sending, and so they stay with one cell serving them, no carrier aggregation, and they get less throughput. And so part of the game is being aggressive enough. Next slide. Mobile users, as you would hope, we really shine because we are quickly adapting to changing wireless conditions. So these are time series of throughput and latency. We're comparing us versus BBR. So this is a trace replay. If you look at the two right-hand side graphs, ours is in the middle and BBR is to the far right. And what you see is when the channel fades out, we are quicker to grab, and fades back in, we're quicker to grab that bandwidth back, that capacity back. And so we perform better as a whole. In addition, um, in terms of what BBR is doing, BBR is experiencing much more delay because it's a bit too aggressive when the channel's good at sending. And so our precise congestion measurements are letting us operate with less delay. Those are the red data points. Less delay than BBR. Next slide. Okay, so if you look at same thing, same kind of situation happens when you compete with an on-off traffic source for the same reasons. We're able to grab the bandwidth quicker. Next slide. And then finally, fairness, thinking about fairness. Can we, for example, can we coexist with other TCP-like congestion control algorithms? And the answer is yes. And you can see that when everyone's talking all at once, we're able to quickly grab just our fair share of the bandwidth, just like BPR and Cubic do as well. So next slide. Okay, so I'll wrap up here, and looks like I have time for questions, which is great. So, so this is basically the first end-to-end congestion control that we know of that seamlessly integrates client-side wireless capacity measurements into end-to-end congestion control for an exact congestion control like scheme. And looking forward in 4G, 5G, massive MIMO, coordination between cell towers, all this stuff, I think that property of what we're doing is going to become even more important with 5G new radio, and as more the most sophisticated versions of 4G get rolled out. In terms of experiments, we outperform all the leading congestion control algorithms in latency and throughput at the same time. And so we have this simultaneously, we get slightly more throughput than BBR. BBR is the most aggressive of all the congestion control algorithms. At the same time, we reduce latency, by 1.8 times, a significant amount. So we're as aggressive as BBR while keeping latency low. And so that's kind of the new experimental result here. So with that, I just want to say I'm really honored to have been here to give this talk at the Distinguished Seminar Series. Thank you very much for listening, and I'm happy to take questions.
Thanks, Kyle. That was a great presentation. I'm sure everyone else enjoyed. Well, I guess we can't clap, but yeah, I'm sure everyone is clapping their own end. So we have actually a lot of questions, so I'm going to read them. So the first question is there a way to come up with an upper bound on the performance? For example, how much more benefit may be available with an even better algorithm? So that's one, I guess.
That's a good question. Yeah. Okay, so let me think about that. So how much benefit? So if, in terms of what's going on the live internet, that may be hard because you don't know everything that's going on in terms of every single queue. What would be, I think what your question is inspiring me, thanks Ashley for the question as well. So what your question is inspiring me to think about is, if you had a controlled simulation environment where you know the capacity, exactly, and you know everything that's going on every single hop of a multi-hop network, that would be an experimental environment that would give you like an optimal upper bound, as you're asking. Um, so that's an experiment we haven't run, but I think I'll take that as a great suggestion for an experiment we could run. So thank you for that. And then that kind of just also tangentially that raises the question of how do you compare fairly two congestion control algorithms. And so a trace and replay is the way we do that. And so I'll just mention that as a tangent. But okay, but thanks for the question. I don't know if that doesn't answer, you can also follow up in the chat.
Well, this is Ashu. Yeah, thanks for taking the question. I guess, is there a way to say if all things being held constant, and the only thing you can do is endpoint measurement and control? Is there a way to come up with just a bound for that? I think that's essentially how your design is, right? You're not measuring the internals of the internet. You only get to measure the edge. And
Yeah.
yeah.
Okay. Yeah. Right. So another thing you can do, and I think we have done this. I don't think I have results, but you can also measure the available number of physical resource blocks, wireless physical resource blocks directly. And so so in terms of, right, so that gives you how much wireless capacity, and with the assumption that wireless capacity is the limiting factor, then that would give you the end-to-end capacity optimal as a function of in time. But that does make the assumption that the wireless capacity
is the bottleneck. Yeah.
Yeah.
Thank you.
Yeah, thanks for your question. Yeah.
Okay, so next question is from Edward. So he thank you for the great talk. I guess Edward can also have access. So I assume all the results were for data downloads. Can you comment on the data upload case and if any different issues?
Yeah, great question. So yes, so those results were all downloads. I believe we also ran uploads, and really for all the same reasons, uploads, let's see. Yeah, for all the same reasons, I believe we would get similar results. I don't have extensive performance results for the data upload case. I wish I did, actually. But
I was wondering too, if on the upload case, whether the client might be able to cheat a little bit and not wait for the axe coming down, and just because you mentioned how fast the wireless channel can change, yet this RTT to get the server to respond. But in the upload, I was thinking you might even do better if you violate TCP a little bit and just dump some data in when things get good.
Good point. Yeah. And thank you for the suggestion. That's an excellent point, right? Because in the upload case, the sender is at the wireless link, of course, and so it can react even faster. And so that's why performance could be even better. Yeah, we have not. It's actually it could be the easier case, and I think the next thing we will do is explore that. The other question I've gotten that is in the same spirit as yours, Edward, is could in the download, now going back to the download case, could the mobile user cheat and inject, say, I want more capacity? And the answer is yes, it could. And so we're also thinking about ways that users can snoop on each other and detect this cheating. But yeah, it is an issue. So yeah, thanks for the question.
Thanks.
Okay, actually we have 4 more questions, but I guess that's as far as we can go because we're out of time. So the next question is from Mariam Khalid. She has 2 questions. Please clarify what happens if the mobile device misreports the capacity measurements to acquire.
I'll be very quick. That's what I just touched on. So indeed, this can happen, and but clients can kind of police each other.
Right. And the next one is the battery overhead.
Right. And great question. And it's not much more processing than what the firmware already does, so the battery overhead will be incremental. But great question.
Okay, so I guess the next one is just a clarification. From Chiaye, she says, why is the retransmission delay 8 milliseconds?
8 milliseconds. It's to give the receiver enough time to decode, to do the computational processing required to decode the frame, and it needs that much time, and so it needs to allow other the link layer needs to allow the next data to be pipelined and received during that 8 milliseconds to keep the wireless medium busy. So then it needs to like assume that that receiver's data is going to go over the air. So then that pushes the retransmission forward by that amount, 8 milliseconds. And so it's because of the computation that the retransmission needs to be some number. They chose 8 because it fit their it fit the processing requirements and the physical resource block subframe length requirements as well, if that makes sense. So that's a great question, and it's the way it's designed to keep the wireless medium busy.
Okay, so the last one, well, I guess 3 more. So it says, you mentioned the last hop wireless capacity varies at the millisecond scale, but the end-to-end link from client to server could be tens of milliseconds. So is the adaptation from the server side happening at the millisecond scale, or is it otherwise?
Great question, and the observation is spot on correct. The adaptation is happening at, yes, but at the millisecond, at the 10 millisecond end-to-end scale. But the trick is that we want the adaptation to happen, because that's the minimum, really. That's the best you can do in the downlink case. And so the game is that we want that adaptation to happen within one RTT and no more. None of this, what BBR does, of, multiple epochs, so each an RTT long, adjusting slowly over many RTTs. We want to be there within one RTT. And typically RTTs today, because everything's on Amazon Web Server, Edge, et cetera. So RTTs today, or latencies today, are typically 10 to 30 milliseconds, because the wide area is kind of gone, because everything's pushed out to the edges of the internet. So that's why it's kind of a good, makes sense from a performance perspective.
Okay, so the last 2 questions are from Shriya Gupta. Does the congestion control algorithm work in case of multiple hops
From cell tower to client? So multiple hops is client relay, and that is that's not deployed yet. It's been talked about for a decade, but it's not deployed yet. It might be part of 5G. It might even be part of 4G, but it's not widely used. So that could be in the future, but not quite yet. Not quite there yet. Multi-hop relay.
And I guess the last one is the hidden terminal problem, which is actually, I guess, more in the case of LTE cellular networks becomes like intercell interferences in wireless communication have any effect on the capacity estimation algorithm?
Yeah, so I'll read that question as, does intercell interference? Because hidden terminal is, really we think about a CSMA network when we talk about hidden terminals, where it's a real collision that's going to cause damage, whereas cellular networks are allocating OFDMA resource blocks so that there isn't much of a quote hidden terminal problem in these kinds of networks, but there still is intercell interference. And so while it's a great question, there still is intercell interference, and it will impact capacity. And so, this work, we have not explicitly taken intercell interference into account in our calculations, but we could and we should, and that's a very good next step. So thank you for that question.
Okay, I guess we're out of time. We took away a little bit of your break time. I know you have meetings, a lot of meetings as well.
Okay.
But I would like to thank you really for joining us today, Kyle, and I very much enjoyed, and I'm sure everyone else did.
My pleasure. Great. It's been great taking all these insightful questions, and really my pleasure to be here.
Right.
An honor to be here.
Perfect. And I would like to thank everyone else as well who joined us today.